I'm Luciano Lucas. Very nice to be here. Very nice to have this opportunity to talk with all of you about a concept, really. So I wanted to share this concept and get some feedback from you. The short story is deep learning is great, but it often requires a lot of training data, or you have pre-trained learning models like what was just shown in the previous talk. But it would be great if you could do something that learn from users directly and has some sort of passive learning. So it doesn't require you to do everything yourself. You can just do what you normally do and the software learns from you. So that's the summary of the whole presentation. Now I'm going to give you some more details and give enough space for you to ask questions or give me some ideas actually how we can do this better. Myself and my team are responsible for all the image analysis that is coming out of Leica. We just joined about 1.5 years ago. We used to be a separate company called S-Vision based in Seattle. Now we're a little bit spread all over the world, and I'm responsible for that team within the Leica group. Right, let's see if this progresses. Next here. Right. Beautiful images, right? That's what we all love to do, create these images and then try to get as much meaningful information as possible. And while some images are relatively easy to analyze, like nuclei, or even if they're packed, others are a lot harder, like neurons are particularly hard because they can be, the morphology is complex. They can be very large, they can be connected. So it's really challenging to do analysis of this type of data. We can do the simpler image analysis, but we know that there is a lot of value. I'm looking for my mouse, it's gone. A lot of value in extracting meaningful information out of these complex data sets. So we invest a lot in this, in creating some algorithms that are either machine learning or standard algorithms that will help us do the analysis. But this takes a lot of time, typically many hours per data set. And I actually tried to estimate this for the whole community, and you can read the text there how I estimated that. But my estimation is that it's something like 304 work years for the neurosciences community. That's how much time that community spends tracing neurons, either automatically or semi-automatically or manually. In total, that's something like that. So it's a lot of time. And it requires a lot of interaction with the software. Seems like I have a call coming on my phone. Hopefully you can't hear it. Okay, so the softwares are pretty complex, right? All these softwares that you use. Oh, my dog doesn't like it. Just a moment. Okay, back. Mailman is at the door. So what I was saying is the software, all the softwares actually are pretty complex. They have this cockpit approach, and users need to learn it, need to master it, and then click lots of buttons in order to get to some sort of result. Even if it's a pre-trained deep learning model, like what you saw a moment ago, and what that we have also, you still have some parameters that you have to set up. You still have to do some training potentially, or at least learn how to use the software so you can apply it. In the future, we think that will change. It will be a lot more automated. But what is the path between, or the points between that cockpit approach and this much more automated approach that doesn't require the users to do that? So this is just a reminder. I think most of you are familiar with that. The top view is, let's say, standard algorithms. The bottom view is machine learning, where you don't really need to have predefined algorithms that will do the analysis for you, but you can provide just some ground truth, typically in the form of annotations, plus the raw data, and you get the rules to do the analysis. This is very time consuming. It can be also very narrow in application, so it will be very good for a specific case, but not so good for the next case. It's not generic. And that's where we kind of started that journey. we did a lot of work starting from 2016, trying to test models that are good for segmentation, but it's very hard to get generic models, to get to a point where you can really apply a model to many different data sets. And generically, that's what it looks like. So you get ground truth, you have the raw data, you train the model, and then you can apply it, and it works well for narrow cases, not so well for the next case. So this is not the concept I'm talking about today. It's a very different concept. What I'm talking about is not, this would be, let's say, manual learning. You would explicitly teach the deep learning model, in this case, to learn what a cell looks like, and it will work for that one cell. What I'm talking about today is actually passive learning, where you look at what the users are doing in the software all the time and learn from those interactions. So the metadata is important, the telemetry is very important, and the image data is also very important. You'll notice that I mentioned is just internal data that we've used so far. So what we do is take all of that information, pair it up with the raw data and with the results that the users get, and we can then train a model that can predict what are the needed parameters for the segmentation to work. We can do that for regular algorithms as well as for machine learning algorithms. And the key part is this image fingerprint. So we condense down the images from complex biological elements down to a fingerprint that looks a little bit like a barcode. That, together with the telemetry, gives us the needed training data to train a model that then can predict how to analyze the images. And in essence, bypass the GUI. So the GUI looks like that in Avia, where you have sliders, you have fields that you put in. You don't need to put anything in, press one button and everything is predicted. All the parameters are predicted, and then you can just apply. Or if you trust it, you can just let it apply in batch to many data sets. So the type of saving, I jumped a little bit the slides. Okay, so the kind of saving in terms of time we found is about 70%. So this is the number I showed you at the beginning. We calculated and ran it on many data sets internally, and we found that we can get that down by about 73% of the time. So in that case, for the neuroscience community, it would go down to about 80 hours, which gives us time to do many more other experiments or spend time writing papers. So this is a beautiful marketing video created by our marketing team. So what does that look like? This is a small data set with neurons. There's just maybe 15 neurons or so in there. You press the button, it predicts the parameters for you. This is pretty much real time. And then you can apply. The apply part is not real time. That would take maybe a couple of minutes to apply on this data set. And you're not applying a deep learning model at that point. You're just applying a regular algorithm, thresholding with, it's actually voxel scooping. But the deep learning model that we train is to predict the parameters that go into that GUI, that interface. So that's the concept. We're testing it out on many different applications. We've done it for 3D objects, standard like potato-shaped objects, for neurons that are much more complicated, and we're testing it out on other things like complex cells and tracking exercises. Avia itself has a lot of other functionality. I'm not going to talk about all of that today, but there is a lot more that it covers. And we continue to work very closely with the rest of Leica to bring more of that functionality with the rest of the portfolio that we already have. Recently, Avia 11 was launched, so you can have a look. It includes a new workflow manager, support for multi-well plates, and additional integration. We already had CellPose. Now we have an even better integration with CellPose. We integrated maybe 2.5 years ago, and now we have a second version, and also now a connection to CytoMap, which is a really great tool to make some of the more advanced, exciting charts like UMAP and Disney and other clustering algorithms and then charts. Big thanks to the team. This is part of it, not all of it, but all of the team that is fully dedicated to Avia. I think I stop there. Thank you so much. Questions, comments, suggestions?